So in question number 23 we are talking about some relationship between Nash equilibrium and certain other concepts. So it mentions that in a non-cooperative game, so a non-cooperative game is basically where players do not cooperate with each other. So our general games are non-cooperative games. Cooperative games are something that we have not dealt with in our syllabus because it's not part of the syllabus for master's entrance. It is something you learn at your master's level. In any case, they say that a Nash equilibrium. So let us go by option to option. So in option number 1, we say that a profile is Nash equilibrium, then it is equilibrium in dominant strategy. So 1 is false. So when it is false, it is sufficient to give a counter example. So counter example is in Battle of the Sexes. In Battle of Sexes, no Nash equilibrium is a dominant strategy of dominant strategy equilibrium, because the dominant strategies don't even exist in Battle of Sexes. In second case, a Nash equilibrium is subgame of perfect Nash is false. So refer to questions 21 and 22. So in the previous questions we saw that in question number 21 here we had two Nash equilibria, LLU and LLR, LLU and RU, whereas only one of them was subgame perfect Nash. Okay, so the set of, so not all Nash equilibrium need to be subgame perfect. Okay, so option number 3 is a Nash equilibrium, then it is a sequential equilibrium. Again, third is false. So in Battle of Sexes, both ballet and boxing are Nash equilibrium, but only one of them is a sequential equilibrium, depending on who plays first. Okay, so if wife plays first, then the only equilibrium is ballet, because the wife prefers to go to ballet, so she goes to ballet. Husband has no option, because if he goes to boxing he gets 0 payoff, right? So I'll just add the Battle of Sexes example here. Battle of Sexes, so the wife is the role player, she can go to ballet or boxing. The husband is the column player, he can go to again ballet or boxing, and the payoffs here are going to be 2, 1, 1, 2, 0, 0, 0, 0. Right, so if you build this as a sequential game, then wife will always choose to go to ballet and vice versa. Let's look at option number 4. So in option number 4, if an equilibrium is an equilibrium in dominant strategies, then it is a Nash equilibrium. So fourth is true. So so here if we are claiming something to be true, then we cannot give a counter example, so we have to give a proof. So let me give a proof. So let SID be a dominant strategy for player I. Then SID, sorry, utility of ith agent for SID given S minus I is greater than or equal to utility ith player for any other strategy Si comma S minus I. Okay, so so given any other strategy profile, given any strategy profile for other players S minus I, so for all S minus I, okay, so for all S minus I, SID, that is the dominant strategy for ith player, gives him the highest utility. So then utility of ith player sorry, what is the definition of a Nash equilibrium? So then then the Nash equilibrium has to be Si star equals to SID for all I. So if all the players I have dominant strategies, then the Nash equilibrium has to be this, because the definition of Nash equilibrium is that utility of ith agent given Si star comma S minus I star is greater than or equal to utility of ith player given Si comma S minus I star for all Si. Okay, so as long as other players keep playing their Nash equilibrium strategies, you get the best by playing Nash equilibrium. So this can be true only if Si star, okay, this will be true if Si star is equals to SID. You see, you're saying that Si star should give him the highest utility, but we know that SID gives him a higher utility, because if not, then there is a contradiction. Okay, because if not, then there will be a contradiction. Okay, so since there will be a contradiction otherwise, so that's why this has to be true, and so we can claim that the intersection of intersection of dominant strategies is going to be a Nash equilibrium. So fourth option is true.